Welcome back to Area Diesel Service. So today, episode 2, number 1 most viewer requested collaboration. We're back with Diesel Creek. So if you're not familiar with Diesel Creek, please go over there and check out his channel. We'll drop you a link below. He does some of the best crusty, rusty resurrections and will it runs on YouTube. Great channel over there. Good friends of Area Diesel Service. We have another project for Matt. So in this box is a turbocharger off of a machine that you have probably seen. This thing is a 1964 Caterpillar D8H Bulldozer, big boy. This is a 46A serial number vintage, again 1964, powered by a Caterpillar D342 engine. She's rated at 270 horsepower, 20.4 liters, so we're talking about 1,250 cubic inches. So somewhere in the vicinity of a 50,000 pound dozer, checking in at 59 years of age. That's what it's off of. The story as we understand it, Matt got hooked up with this machine several months ago. The thing had sat for 15 years. Matt put out a video. We'll drop you a link to that as well. They went through the standard Diesel Creek routine and got this thing back to life. When they fired it up the first time, somehow they busted the pony motor off of the engine. If you've seen the prior videos, if you catch it, you can hear when he shuts this machine off, you can hear this dude grinding to a halt.
Jesus Christ. Well, the turbo hitting the housing, I don't know about all that.
Oh, is that what that noise was?
It sounded like it to me.
Oof, that's not good.
Never a good symptom when you're describing your turbo as grinding. This is suspected to be a Garrett T14 turbocharger. Again, old school, right? This thing is no longer supported, with exception of us at Area Diesel Service. You're not going to find service components. You're not going to find replacement units. This dude is dead as far as that goes. We drew the short straw, send it out to Area Diesel Service, and see if we can bring it back into life. So we're going to open this thing up live with you on camera, and we're going to see what I've gotten us into. 90 pounds on 270 horsepower of engine. Today we could accomplish 270 horsepower with 40 pounds of turbo. So a lot has happened in 60 years. The turbo industry is no exception. This thing is fairly antiquated. And for those of you that have been following along, Matt always sends us a letter and a description of the situation. And this one is no exception. This one, Matt says, this one wasn't my fault. Matt did not disassemble this and send it to us in pieces like the injection pump we saw last time. This thing should be in as removed condition. Oh boy. Oh. I can already tell you that the boys in the back are going to be excited about this. Initial inspection. She's been leaking. Perfectly aligned with Matt's channel. Crusty and rusty. Covered in schmoo. In need of service. This thing has also had years of deferred maintenance, if you will. We've accepted the challenge. If anybody can whip this thing back into shape, it's going to be us at Area Diesel Service. So we're going to make kind of an initial assessment here. The turbine housing, super pitted, right? This thing is getting pretty thin. You can see some torch marks where he had to go in and cut the studs off. The problem is there are no components left. So we are basically going to have to work with what we've got. We may be able to find some service components, but as far as hard parts, it's going to be tough. The outlet flange where the exhaust connects to the machine, right? So this is exhaust in. This is up and out the stack. Busted here. Mud dauber nest, right? Par for the course. I don't know if you can hear that. We'll try and get the mic a little closer. Right? So that's the noise that you were hearing when he shut this thing off, right? The engine came to a halt. The turbo kept going. Not good. Never want to hear that out of your turbo. If you're questioning the quality or the condition of your turbo, the crude test is, the first thing, check radial shaft play. The shaft is coming through in this manner. We want to go up and down, right? We're trying to see if the clearance in the journal bearings is excessive. Shockingly, the journal bearings feel pretty tight. The second layman's test is to check the thrust, right? Does the wheel shift this way, axially? I'm pretty sure the microphone's picking that up. That's 1/8 of an inch, maybe 3/16. And there is some clearance in the thrust components axially, but not enough that you can feel it with your bare hand. If there was no clearance, the turbo wouldn't turn, but it's so precise that you can't feel it with the bare hands. Thrust is out, at least it sure feels like that. The shaft is still in one piece. The grinding that we're hearing is all on the turbine end. We can't tell much. The blades, at least the exducer or the outlet of the turbine wheel blades, look okay. So hopefully it hasn't ingested some of Matt's engine. But we really won't know that until we tear it down, right? That noise on his video right there, that's no bueno. Desperate times call for desperate measures. Remember, when this thing was modern technology, I was negative 19 years old. We're going to have to call in reinforcements and find somebody around that knows exactly what we're looking at. So we're going to bring in our founder and president, Val Leafers.
Well, I knew you had to have something old when you called me. Wow, the old girl's got a case of acne, hadn't she?
Yeah.
Nothing just out of line. I wish I was in as good a shape as this is, because we're pretty close to the same age anyway. You've got, well, that's not too hard to diagnose, is it?
Got some thrust wear.
Yeah. Well, very, very typical of what you're going to find in here. Yeah, it's an oldie but goodie. It's not like some of them that are just totally deteriorated away. I think with some tender loving care, we might be able to make a serviceable unit out of it. But you know what? If you look at this exhaust on here and the size of the engine, I think we got probably a turbo that's halfway an example. But this rascal can do the same job that we're doing with that one.
Yeah, it's there's been some advancements.
Yeah. Yep. Well, that's pretty cool. Be excited to get that in the back and open it up and see what's going on in there.
So this is off of a Dozer that was built in '64, right? We opened in '73.
Yep.
Is this something that back in the day was a regular appearance?
Pretty well.
Yeah, these were.
Yeah. This has technology that's probably even back farther than that yet, but a lot of the technology you see in this one came off of some of the turbos that were in World War II on airplanes. And it's going to have a nozzle ring in it, which is held on by these bolts around here. And it's a nozzle ring. Instead of changing the AR of the turbine housing, you did it with a nozzle ring. Definitely not a variable geometry at this point because it's a fixed geometry. Mm-hmm. Well, its predecessor was, I think, a 1402 that had a two-piece bearing housing on it, which was bolted together. So this is a real modern update for the original part we started with. So I'm going to be kind of excited to open up and just see what we can do with this old girl.
It's kind of cool because conceptually, not that much has changed, right? You still got exhaust coming in, running across a turbine, leaving out here, and the same thing over there, right? Air coming in.
Draw it in, blowing out.
Yeah, it's so, conceptually, same thing. But the amount of engineering and advancements that have gone into wheel design, flows, and geometries and all that is just, well, you saw it. That other turbo could do as much or potentially more than this thing. And that turbo is
it's
20
obsolete.
years old. Yeah.
Oh, no,
yeah.
20?
Yeah, or older. What?
Yep.
Yeah.
Yep, considerable.
So,
Well, very neat. I'll be anxious to go back and get my hands dirty on that one.
Oh, our machine shop can do wonders with this.
yeah, so we don't know what we're going to get into, but we may end up manufacturing some components for this. The noise that we're hearing, all right, we said it was axial play. We can tell that when I push the turbine that away, it's not the blades contacting the contour of the housing. When I pull it this away, not good. So we suspect that the backside of the turbine wheel has run up against the backside of the nozzle or the backside of the bearing housing or the heat shield. Does this have a heat shield?
Yes, it does.
Yeah.
Plus that the compressor wheel is going to be ground off because it went that way. Instead of 30 thousandths fit, you're going to have interference fit.
Yeah. Is this from the Labyrinth seal era?
Mm-hmm.
Right, so this thing doesn't, is that on the turbine end?
Turbine end, yeah.
Right, so we've talked about it before, but the turbine end runs a butt-cut piston ring on modern turbos. This dude is of the era where there isn't a seal. They kind of cut a thread, and just the direction of the thread is chasing the oil opposite.
Keeps the oil in.
Yeah. So it's almost like it's engineered to leak, but they cut this thread so the oil comes back where they want it to be.
And then there's enough oil that burns, which forms carbon, and then that carbon gets around that particular seal and really makes a pretty good seal on it.
So this would be out of the box, might leak a little, but by design, right? Take it
It'll
out.
quit.
Yeah, take it out and load it up and work it, and it'll seal up. Self-sealing turbo. Yeah, it's come a long way.
Well, I'll let you carry it, okay?
I have no doubts. and again, can't get the hard parts, right? So you may see not only the repair of a turbo, but you may see the repair of some subcomponents. We'll scrounge and see. Again, we don't even know what we need yet. If there's any out there, right, we can find it. We've got those connections, but that'll be a challenge.
We're ready for it.
We're going to get this thing written up on a work order. We'll transfer it back to the turbo department. Sometimes those folks are a little camera shy, so we might just be given updates throughout the process. If we can get them to allow us to capture their work, we'll certainly bring you along, show you what it's going to take. This is going to be a fun one. Again, this is obsolete and not supported, so rebuilding it back to a quality standard is going to take some effort. Also, while we're up here, this opportunity came to us as a viewer suggestion collaboration. Without the help of you guys as the viewers putting these opportunities together, we wouldn't be able to bring you this type of content, and we appreciate that. With that said, in other people's videos where it looks like they could potentially use our help, tag us in a comment, take a screenshot where you did that, and email it to us at parts@areadieselservice.com. We'll throw you a hat and a pair of gloves, right? Send us your name and address. Show us a screenshot of where you shared us or recommended us. We'll throw you some swag. That's enough of that. We're going to get this thing tagged and written up back to the turbo shop. We'll bring you along and see what we can do. We're back in the turbo shop. Val has given this thing the official judo chop. We've got her scattered on the bench, and we've made some initial observations, okay? We've got good news and we've got bad news. Bad news is, it's pretty bad. We're going to go through what some of the issues are, but the good news is that we're pretty confident we can fix this thing. We're going to start on the turbine end and just kind of walk through what we're seeing for some of the issues, okay? First thing, the outlet flange connector. You can see a couple of bolts. This is where the exhaust connects. Got a split busted right there. Pretty gnarly, so that's going to take some attention. Overall condition of the turbine housing is crusty. She's pitted, she's bad. Limited options here. We're going to clean it up and see what we think. Also, where it bolts to the exhaust manifold, the surfaces are not flat and true. Going to take some work there. Biggest issue is in the surfaces where the rest of these components mate together, right? So this surface is critical. This component fits in there, and we had a pretty significant case of rust jacking, right? This thing started to come apart and rust, and it split and it grew, and it's gnarly and nasty. Perfect example of some crusty rusty for Diesel Creek, but this is not where you want your crusty rusty. These are critical dimensions. So that's whammied. We're going to have to probably do some surfacing here. Surfacing here, we may have to come up with some shims or additional material to make up the difference. This is the nozzle that we briefly spoke about at the parts counter. It's actually in pretty good condition. Turbine wheel. This is a critical area here. This is the journal where the bearings ride. It's actually in pretty fair condition, and we haven't cleaned it up. We haven't taken any measurements. We don't have any contact on the turbine wheel to turbine housing fit. Clean it up, do some measuring and inspecting, see what we can do with that. Heat shield doesn't seem to have the same rust jacking issues we looked at earlier. Bearing housing. So when the rust jacking occurred, and you can still see some of the shims we were looking at earlier, you can see here there's chunks of it, right? So this thing grew. Again, we haven't cleaned up and inspected, but we suspect that this surface is no longer flat and true. Going to take some machine work there. The journal bearings, again, need to clean up and be inspected and measured. While they're dirty and while we're looking, they don't look terrible. All right, so the grinding that we were hearing at the parts counter, the grinding that you were hearing on Matt's video, the thrust play that we discussed is here. Right, so I don't know how well this is showing up, but that dude is chewed up, as is this thrust component. So, like we discussed, this is what's controlling axial play inside of the turbo. This is the labyrinth seal that we discussed. Kind of looks like threads on there. These components are hammered. Dunzo there. Back plate looks all right. Here's a bag of struggle bus, right? This is the crusty, rusty bolts that busted and stripped trying to get this pig gutted. So we're going to need a little bit of hardware. No big deal. Because the thrust was out, it allowed the compressor wheel to come up and contact the compressor housing. It doesn't look terrible, which is fortunate because you couldn't get one of these if you wanted to. Fortunately, the design and the configuration of this turbo calls for a shim to set the stack-up dimensions. A shim goes on the back of the wheel. That determines the relationship between the compressor wheel and the compressor housings. We've lost a little bit of material on this wheel. It's going to take some manual labor. We're going to clean this thing up, balance it, take a deeper look at it, but we suspect at this point that this wheel can be saved. And we're just going to have to compensate for the wear here by stacking the wheel deeper into the housing. Again, too dirty now to know for certain, but we don't think that's going to be a problem. Component availability likely to be a challenge here. We discussed at the counter this thing's no longer supported with exception of what's left at Area Diesel Service. Believe it or not, I couldn't believe it. We had in stock a new seal insert, a new thrust component, so those components that were hammered that we looked at. So we've got those brand new. I'm shocked. Journal bearings. We had two different sizes of journal bearings. So we talked about the journal on the shaft. If this is not acceptable, we'll have to machine this undersize and then use a custom bearing, right, to take up what material we had to remove. And then the same thing is possible inside the bore of the bearing housings. We don't know what the journal in here looks like yet. Standard operating procedure is, if it's whammied, take some out, put a hone on it, get the surface finish good, and then take that up with an oversized bearings. We need to clean this and inspect it to really get a game plan. If we've got to machine here, we've got to make sure that we can come up with an appropriately sized bearing. Fortunately, we're going to get to see some of the machine shop in action with this thing. We're scattered. Now we've got to clean it up, do some measuring, do some final inspection, and then we'll get a game plan. We'll talk about components or component availability and or solutions for those issues, and we'll bring you back. Step 2 complete. We'll see you in a little bit. We're back in the teardown room. We've got what's left of Matt's turbo here in the basket. We're getting ready to move this thing in throughout the cleaning process. This contraption here is a Peterson bake oven. We're going to load this basket into this oven. We're going to run this stuff at 600 degrees. We're going to run it for about 6 hours throughout the course of the night, and we're going to cook this stuff down, right? We're trying to get rid of the schmoo and the grease, the oil and carbon. We're going to bake this stuff so that when we move it over to the blast cabinet, we don't ruin the media. So we're going to load this thing up, and we'll show you what happens when it comes out. All right, we'll show you what it looks like when we're done. Still a little warm. Oh! Would you please? All right, here she is. So again, we went 600 degrees for 6 hours, point being to try and solidify the schmoo, and we've done just that. So this was all grime, wet, greasy grime. And now you can see she's just busting right off of there. Bearing housing also just turns it to powder, crumbles right off. That's step 1 in the cleaning process. We're going to take these components, we're going to move them over to the blast cabinets. That's next. We're going to start these with the most abrasive material. It is terracotta and quartz mixed together. That's going to get us through most of the gnarly stuff that's left on these. And then we'll move at least the aluminum stuff over to glass dust and give those a once over. Baking is done. We're going to move it on to the next step in the cleaning process. So we'll bring you along. So this is the blast cabinet side of teardown. I know it's kind of a dungeon in here, but it's a necessary evil. We're tearing down hundreds and thousands of crusty, greasy, grimy turbochargers, and this is where we do it. Just it is what it is. It's a dirty process. It's how we've figured out how to accomplish it. So we're going to take these components, move them into these cabinets, and when they come back out, we'll give you another look at them, and then we'll take it from there to the next step. So we'll bring you back. I got a phone call from the turbo shop. They have some news or findings to report. I don't know much other than they weren't very good. This is the turbine housing off of Matt's turbo, right? So we followed this thing through, tore it down, disassembled it. It is now cleaned up and the inspection has been performed, right? This thing's pretty gnarly. We knew quite a bit when it was still assembled and together from our inspection that it was not in very good shape. Even when it was dirty and before it was cleaned up, we could tell that rusted and pitted to the point where a lot of the original material is just completely gone. Now that they've cleaned it up, we can take a closer look, and they already found bad news, and it might be hard to pick it up on camera, but right here is what we refer to as the tongue. So that is almost the direct point of entry where the exhaust gas is first introduced to the turbine wheel. It is probably the most highly concentrated area for exhaust temperature or heat, and this dude is cracked. And right there, if the camera's picking it up, there's a hairline crack, and it goes plumb through to the other side or the outside of the casting. So right here, probably hard to see on camera, but this dude is, you know, maybe 1/8 of an inch thick. It's just so much of the original material is gone away. There's not enough meat left for us to do a braze job. That's something that we do regularly, right? Just like you've seen on A-Bomb or Keith Rucker, we grind that dude out. We do a TIG braze, but it is possible to braze and repair these housings. But this dude, at this point, I'm going to say has reached end of life. So there is no serviceable life left in this component, which is unfortunate. Okay, we've spoken a couple of times already. This thing is no longer supported by the original equipment manufacturer. This is a Garrett unit. This thing's 60 some odd years old. They don't support it anymore. The aftermarket supported this unit for many years. It's so old that the aftermarket doesn't play with it any longer. Potentially a devastating blow to the Diesel Creek turbo repair. I don't know what we're going to do at this point. I'm going to go back up to my office. That's kind of what I do, and see if we can't find another solution. If not, into the scrap heap she goes, and Matt's going to have to find a plan B for his engine. So don't know where this is going to go from here, but we'll bring you back when we have a plan. You saw in the last update that we have a turbine housing issue, and we've mentioned before that we are Class A hoarders. This is where the majority of the hoarding happens. This is the core storage facility for area diesel, at least the cores that aren't going to be required in short order. This is the long-term storage solutions. Pretty good behind the scenes. You'll see here everything is fairly organized as far as dirty cores and components. We're looking for box 54. Theoretically, box 54 has 2 of these turbochargers, both in graded condition. They should be acceptable on the compressor side and the turbine side. We don't know when we got them, where they come from, but they are in the archive. There should be 2 of them in 54. So we're in the 100s here, over to 70. Number 1 up here, 54. So tucked in the corner, we're going to pull it down and see what we've got. Cannot believe it. There she sits. That is a spitting image of Matt's turbo. Yeah, it ain't the prettiest thing, but there's just not any of this stuff out there. So the head of the turbine wheel is completely gone. This thing might also be a boat anchor. We're running out of options, so we're going to take this turbo. We'll take it back over to the other facility, and we'll yank that off and see if it's going to be any good. At first glance, it looks better, but again, turbine wheel is completely gone, so it likely got into the turbine housing. We'll get this thing loaded up, and we'll bring you back once we get this one torn down. We'll check back. Can't believe it. Take that back to the other shop, see if we can make any good out of it. Plan B on the operating table here. These guys have scattered it. Obviously, we have not finished the cleaning process, but we're trying to get preliminary inspection completed to see if this is potentially a viable solution for the components we were not able to harvest out of Matt's turbos. This turbo, when we looked at it, we went and picked it up from the core house, and we could tell that it had experienced catastrophic failure. This is what's left of the turbine wheel. You guys saw the turbine wheel out of Matt's unit. This one had a high-speed come apart, catastrophic failure, and it got into the turbine housing that we're trying to save. Right in here. So this is where the contour of the turbine wheel rides. Looks pretty bad, but we think we can work with this, okay? There are no components out there. We can't buy a turbine housing. This one, even though it looks pretty nasty, it's considerably better than the one from Matt's turbo. The pitting is, it's hard to say that this is good, but this pitting is less than the pitting on Matt's turbo. The meat, where we were talking about the crack being all the way through on his housing, there's probably 3/8 of an inch of material left in the tongue area. So this thing still looks pretty nasty, but it's a far cry from the condition of the one that came off of Matt's turbo. Also, we spoke before about the compressor wheel. Even though this turbo experienced a catastrophic failure, the compressor wheel did not. We need to clean this up and do an inspection, but it looks like it's probably in better condition than the one from Matt's turbo. Bearing housing, don't know. We think we can salvage what we've got from Matt's turbo. This one potentially is in better condition. The surface where the turbine housing meets up with the bearing housing is not nearly as pitted, and this one, the shim in this one also deteriorated, but it still looks to be fairly flat. So don't know there. Heat shields both got hammered when the turbine wheel exploded, and compressor housing, we didn't look at it too deep. Matt's compressor housing is good, but this compressor housing looks okay as well. That's where we're at for now. We're going to run these through the rest of the cleaning process, and then we'll get all of the components back together, and we'll have an actual game plan for what we're going to do here. So we'll bring you back yet again.
Then it could be letting it walk out too far. Now, it's not going to walk out 1/4 of an inch or 1/8 of an inch anyway. It's going to be a 20, 30 thousandths to do that. There, and it contacted and made this groove in it here, and that's all because the thrust was out of it. So if we get the good thrust, and we determine that this bearing that's here won't walk in and out on us, then we've got that licked.
So you followed us through some of what we're going to call phase 1, right? Disassembly, cleaning, and inspection. There's been a few curveballs throughout the process, but we now have what we believe to be enough material to go back together with a new turbo for Matt. First thing, why did it fail, right? Why is it here? We heard on his videos this thing was grinding. Right there. That's no bueno. We inspected it at the parts counter. We found axial play, right? So we knew the thrust was out. Now we've got it disassembled, cleaned up, and we can see what's going on. The failure that was presenting the symptom was in the thrust components. What we have is classic textbook oil contamination. So it looks like somebody threw a handful of gravel in this thing, and the oil contamination chewed up the thrust components. And that's the, we talked at the counter, we had a 1/4 inch of axial play. That's because the contaminated oil wore these components so severely that we developed that amount of end play. Along with that are the journal bearings. So these are the bearings that ride on the OD of the shaft and in between the ID of the bearing housing. Theoretically or factually, this turbine wheel rides in a film of pressurized oil. So there is no metal-to-metal wear inside of a turbo, but the journal bearings on the OD show significant signs of oil contamination. Grooving on the OD of the journals. Surprisingly, the ID looks pretty good, and the OD of the shaft looks pretty good, right? So there's centrifugal force on these. The contamination would tend to want to gravitate or go towards the OD. When it did that, it also got into the ID of the bearing housing, so it is grooved significantly. The surface finish is beyond salvageable use. It's going to require some fixings. We've got all of the parts scattered up here. The three wise men met back in the machine shop and discussed these components and the required repairs, and we've got a game plan. So we're going to kind of step through each component, talk about what's going to happen. Things are getting ready to get exciting, right? These components are getting ready to split up and head back to the machine shop. So unlike an injection pump, which you may have seen us do before, injection pump technician takes that one product cradle to grave. They walk it through cleanup, tear down, disassembly, inspection, rebuilding, calibration. One person, the entire process. The turbo world is a bit different. We've got folks that are in disassembly. We've got folks that are in cleanup. We've got folks that do the inspection, the machine work, the reassembly. So this thing splits up and goes through many different paths throughout the remanufacturing or rebuilding or repairing process, and it'll come back up to a single builder, and this stuff will all get slapped back together. Enough rambling. We're going to take a look at some of these components specifically. Turbine housing. This is the unit off of the turbocharger that Matt sent us. We've already done a review on this thing, but again, cracked in the tongue, too thin to braze. The rust and corrosion severe. This thing it's done, right? This can no longer be repaired. This is headed for the scrap bin. This was the outlet connection off of Matt's turbocharger. Bolts on here, and this is what the exhaust system connects to. It's cracked, it's corroded, it's pitted. We're going to have to make this. We'll get this thing drawn up, get it recreated. This is the turbine housing off of Plan B. It has been baked and blasted. We didn't bring you along for the cleanup process, but you saw some of the teardown for this unit. It's hard to say that this is better, but it really is. It's still not what we would like to put out. But again, guys, this thing's 60 or 70 years old. You cannot get these components. It was a miracle that we had a core on hand. This is the better option to get something back out to Matt that's going to run. So it's going to need the hardware removed and drilled. Same thing on the flange where the bearing housing meets up. It was a struggle to get this thing apart. Most of the hardware busted. This thing will have to go into the machine shop, get the hardware drilled out, rethreaded, heli-coiled possibly. A little bit of work there, not a big deal. The big deal is the damage. So we discussed that the turbine wheel was gone from this core turbo. When it came apart, the turbine wheel got in to the bore of the turbine housings. It's probably too significant for a buff job. A lot of work needs to happen there. Face it on the inlet. Same thing with the hardware here and here. We'll take you back to the machine shop and let you check out some of that. That is the turbine housing. So we talked about on the boat anchor housing, it's got the big crack all the way through. It's in the tongue area where the exhaust temperature is most concentrated. We're not real happy about the carnage on the bore of this thing, but this turbo operates with a nozzle. Okay, this is a changeable component that dictates the speed at which the exhaust gas is introduced into the turbine wheel. So if you want it to run harder, change the nozzle ring to something that's choked up tighter. This component is what determines how the exhaust gas meets the turbine wheel. So yeah, the contour is bad. We're going to have to work on it. But in reality, where the rubber meets the road is between this component and the turbine wheels. We can fix that. That's what we do. It's less than desirable. I wish we could get a brand new turbine housing, but we can't, right? This is the real world. This is what we're going to have to do. Fix this housing. We're fortunate that we had something a little better than what he had to start with. This is the turbine wheel from the Diesel Creek Turbo. It actually is in fantastic condition, all things considered. This turbine wheel and Matt's bearing housing were of standard specification, so these components had not previously been machined. The journals, where the journal bearings ride, one here and one here, are in fantastic condition, especially considering the contamination issues that are apparent on some of these components. It's currently at standard spec, so again, has not been machined. We are going to polish and see what happens. We will likely grind this undersize, so not unlike a crankshaft, right? You've seen or heard 1010 on your crank journals. Same thing. We will grind this undersize back to a quality finish, and we'll get a custom bearing that makes up the difference. This thing also destined for the machine shop. They'll do some work on the journals. If that doesn't work, we actually had in stock a remanufactured turbine wheel. This is off the shelf. It has previously lived. It's good to go for another cycle of life. This one has been machined already 5 thousandths under on the journal. So if we can't save Matt's wheel, which there's no reason to think we can't, but if we can't save it, we do have a plan B for that. Again, the turbine wheel out of the core that we had, it was gone, right? So we can't save that one. Bearing housing. During the teardown process, we talked about the shim that had deteriorated, and we talked about the rust jacking, right? These layers of shims had corroded so significantly that they spread apart and caused some damage. Those shims cannot be purchased. So this stack of shims is something that we farmed out to the machine shop north of us. They got a fab shop up there. They've got a water jet. We drew out what this shim stock looks like, and they made us a selection of different thicknesses and different shims. When we do the repairs, if we've got to remove material from this now pitted and untrue surface, we now have the shim stock required to effectively put that material back where we have machined it. That was a hurdle. Not a big deal. We've got a solution. The bearing housing. So we've got two of them. This one was Matt's. This one was out of the donor turbo. The journal, where the OD of the bearing fits into the bearing housing, is scored. That's where the foreign object, or that's where the oil contamination was most prevalent. Standard operating procedure is to hone that out, go to a larger OD, again, custom bearing to make up the difference, restoring factory clearance specification. This turbocharger, Garrett T14, throws a little bit of a curveball in there. Generally, in most turbo configurations, this journal bearing is captured by two snap rings. You pop one snap ring in a groove in the OD of this bearing housing, you slide the journal bearing in, and you capture it with a snap ring on the outside. Now it's contained. The way that they designed this or built this, I don't know if you can see it, but there's a step inside of here acting as effectively the inside snap ring. It makes it difficult to pass a hone through there because there's a step that is smaller than the surface area where the bearing rides. Okay, a couple of options. How do we get that grooving cut out? How do we get it to the next nominal bearing size? Two options. We can try and come in with a boring bar and just stay away from the step and hope that we get a good enough finish. Maybe we can do a polish on there without knocking the step out. Second option, cut the step completely out and then cut a groove for a snap ring. Then take it and hone it and fit the journal bearing as we described. Second problem, again, the shim that deteriorated has pitted and warped this surface. We've got a good register here that we can pilot from, that we can machine from. This is known good machined area, so we can chuck here, we can do the bearing work, and then while we've got it chucked off of this known good register, we can face it here and then turn it here so we can spin it around and do the work on the backside. Variety of options. We have not necessarily determined which way that's going to go. This stuff's going back to the machine shop and they will be the ones that actually pick the plane of attack. But again, like we mentioned, the three wise men met at the table. There's 100+ years of experience. If those guys can't figure it out and come up with an effective game plan, I don't think anybody else could either. I'm comfortable and confident this is not going to be an issue. If it is, the bearing housing out of Plan B was in similar condition. We've got a backup plan if needed. The other option we talked about the labyrinth seal area. So if either of those areas don't meet specification, we actually had in stock, this is a machine shop repair component for this 60-year-old turbo. If this area is not satisfactory, we'll machine it out, press in, put a couple Dutchmen in there, and restore that area back to factory specification. We spoke of the primary mode of failure, primary problem with this turbo. That was in the thrust components. These are hammered beyond repair. It's not really something you generally repair anyway. If it's bad, you replace it. That's normally not a big deal if you can get the parts. This thing still blows my mind. This was a brand new Garrett authentic thrust insert in stock on the shelf. Been obsolete for many, many years. We still got them. And the corresponding thrust component that mates up with it, also in stock on the shelf, restoring the factory thrust clearances back in this turbo. This I would have thought would have been the most challenging component to acquire, and it was on the shelf. So very pleased. This is the nozzle ring we spoke about for the turbine housing. It's good to go, cleaned up just fine. Heat shields. So this was out of Matt's unit. You can see a split here. We could TIG this back together, grind the weld back off. I haven't seen the heat shields out of the Plan B core turbo. Maybe they're in better shape. Maybe we'll be fixing this. This one got a little booger there. Not concerned. We can take care of that, no problem. Compressor wheel, cold air side, fresh air side, whatever you want to refer to it as. This is where the charge air, so fresh air from the filtration system, drawn into the turbo and discharged out of here, fed into the engine. And this is the compressor side. We've spoke about this already. We know that when the thrust components failed, it allowed the compressor wheel to reach out further into the compressor housing and contact the housing. Housing's got a little bit of minor scuffing, no big deal. That'll buff out and clean up. Compressor wheel had a little bit of material removed And again, we spoke about the way that this thing goes together. This wheel is shimmed to dictate its depth or relationship to the compressor housings. We could have theoretically salvaged this wheel. We would have just shifted it deeper down into the bore, but miraculously, even with as catastrophic of a failure as we had from the Plan B turbo, the compressor wheel was in fantastic conditions. Absolutely zero contact, no foreign object damage, nothing on the tip of the compressor wheel. This thing's in great shape. So we'll finish cleaning this up. When we get done, it'll look like that one. We've got a better compressor wheel to go back together. Compressor housing, it's been cleaned up. Again, we might do a little buff job on the trim, on the contour. The bolts all look like they came out good. Chase them with the tap. May have to do a Heli-Coil or two, but the rest of the compressor housing looks pretty good considering what we started with. Last thing is the back plate. Not much going on here. This is just what connects the compressor housing to the bearing housing. Very fortunate and thankful to have lucked out and had one of these in core status in the Horde. Without that, this thing probably would have been donezo. This is what we know as of now. As of now, because many of your inquiring minds want to know, where are we at cost-wise? And this is the reason why we don't see too many of these turbos anymore, because this repair is likely going to exceed the value of Matt's bulldozer. As of right now, 5 hours in, $125 an hour, we've got $625 in labor just to get two turbos torn down, cleaned up, and inspected. We also have at this point the expense of the sublet for the manufacturing or production of the shim stock. This was $215 for the material and the water jet labor. And then we also have the expense of the Plan B core turbo. We're assigning a value to that turbocharger of $500. I know that seems crazy, but you can't buy them, and it's worth something, right? We kept it, we stored it, we saved it for a rainy day. Somebody's going to need it. We had one. It's expensive. $500 for a junk turbo. It is what it is. So $500, 6 1/4. We're at $11.25. We had 217 here, so we're $13.50, guys, and we haven't even got into the machine shop, and we don't have a turbo. So not trying to run you off, but this is an expensive project. This is going to end up being extremely expensive, and in most scenarios, going to cause a trip to the scrapyard with a bulldozer, right? Nobody's going to put a $5,000 or $6,000 turbocharger onto a $5,000 or $6,000 bulldozer, except Matt at Diesel Creek. Enough rambling. If you've stuck around this long, things are about to get interesting and exciting. These components are headed back to the machine shop. Some of those folks are a little camera shy, so you might just get a couple hand models and a narrative explanation. Maybe we can coax them into giving us some of their input. You're going to see some of our equipment, which I'm excited to bring to the YouTube world, and we're going to move this thing on to the next phase. So we're going to bring you along. We've made it back to the machine shop. We've got the first component chucked up here, all right? We're in the Enco. This is effectively a Bridgeport clone, and what we're after in this step is the hardware. So you saw us bust all these studs during the disassembly process. We're going to watch the guys go in and fix this thing. First thing we're going to do is come down with an end mill, and we're going to mow down the top of that stud so we've got a flat surface. We'll change out to a center drill. We'll come in and get us a center in what's left of the stud. We'll come back with a drill bit. We might take it in 1 or 2 bites. We'll drill down through the existing stud, and then we're going to tap this for a Heli-Coil. Easy manual machine work. These aren't coming out, so we're not even going to attempt to extract them. We're going to drill them out. We're going to Heli-Coil. We're going to set up for new hardware. All right, so again, the top edge of that stud is not flat and true, and you can't center a drill bit without a flat surface. Step 1, come down with an end mill and flatten off the top of that stud. You can see him there watching, trying to establish a flat surface to work from. All right, he's got her decked off. Going to change tools. We're going to go to a center drill. Now, if we were trying to extract, we'd be super concerned about getting dead center on this. But because we're going to a Heli-Coil, we're just going to eyeball it. Making sure he's got her lined up good. That's it. Just get him a center so his drill bit doesn't try to walk on him. Tool change again. Looks like he's going to go 2 steps on his drill bit. Picked up the small bit first. Little lube job. Not going to get in any hurry here. Going to peck away at it. Again, that stud's been in there for 60 years, so. In small bites, keep her lubed. We don't want to pack a bunch of chips in there and bust a drill bit, so there it went. Drill bit number 1 complete. Drill bit number 2. So this is tap size for the Heli-Coil. He's got a pilot knocked down through it, so this one might eat pretty fast. So he just poked through with his big bit. Change her out. Looks like he might be getting ready to power tap. Going to get exciting. Yep. Looby dooby. So start it good and centered with the mill. Going to drop the knee down. Going to hand tap it from here, I would assume. Trying to get it out from under the spindle where he can work on it. And he's not concerned about staying centered on that hole anymore. He's done with the mill at this point. Got a tap wrench on there. Going to do this manually so he can feel what's going on. We don't want to run the power tap down in there and bust the tap off. Never a good day. Looks like it seems to be cutting pretty good. All right, stud gone, drilled out, hole tapped. I'm going to grab the tool for the Heli-Coil. He's being kind there with his hand and trying to protect us and the camera from the shrapnel and juices. But all right, he's got his Heli-Coil tool. So if you haven't ever seen a Heli-Coil, you just go oversized with the hole and then you thread in a new set of threads. Standard repair for a tapped hole. There she took. All right, so now he's screwing that repair insert down in there. Going to want to make sure that it gets below the mating surface. I'm going to reach in there and right there, bust off the bottom of the Heli-Coil. And that's it. 8 more there, 4 on the back. Thread work, at least on the turbine housing, is complete. It's the same thing over and over for the rest of the turbine housing repair. That's what we're doing there. We'll move on to the next component. Component number 2, turbine wheel. We've got Matt's turbine wheel chucked up in the SuperTech cylindrical shaft grinder. This is a extremely precise machine tool, an extremely critical component and dimensions. During the inspection process, we determined that the turbine wheel showed enough wear where we were going to have to machine it. We have gone to the warehouse and determined that we only have one option for undersized journal bearing. The shaft wasn't that bad. We normally would go in increments of 0.005 of an inch undersize. Those are generally the nominal dimensions of custom bearings. But again, as we've discussed, product support is non-existent. The only bearing we can come up with, short of manufacturing our own, is 0.010 undersize on the shaft OD. Nominal factory specification is from 0.7997 So 0.8 even. Factory tolerance, 3/10,000ths of an inch. We're going to grind this shaft 10,000ths undersize, and we're going to try and land between 0.7897 and 0.790. And again, the material that we remove with the grinder, we're going to take up with a custom bearing. Again, this is precision machine work here. We're going to zoom in and let you watch an expert grind this shaft undersize. And you'll see it happen in probably a number of different bites. We'll get it undersized, then we'll take it over for the last 10th or 10,000th of an inch. It'll be a hand polish, and we're looking for final dimension and surface finish. I'll get out of the way and I'll let the experts do their craft. You'll see him hit both journals with each bite. Parallel or concentricity or the equalness, it's imperative that both journals are done on the same planes. Take one bite there. How big of a bite are you taking? One at a time. All right, so again, we're shooting for a 10,000th undersized bearing. The shaft had probably 1,000th of wear in it, and he's taken bites of about 1,000th at a time. So you'll see the shaft come off after each bite. So he'll knock it down 1,000th, come over, take a reading on it, figure out where he's at. A lot of back and forth. We won't show you the whole process, but he's watching it extremely closely, right? This thing is unobtainium at this point. If he smokes this one, the project is delayed. Cannot order up a new shaft. No pressure on the master, but I have no concern that this thing won't be brought right back to life. Going to dial in another 1,000th of an inch, and he's hand feeding across it. So he's keeping an eye on it. It's the compressor side journal. Walking up on the turbine journal. And he's going to walk it up just as close to the back of the head of the turbine wheel as he can get it. Watching her like a hawk. And there he's done. Come back down. He knows that he's got enough meat. He doesn't have to measure it every step of the way, but he'll keep a close eye on it. Roughly 10 passes across the cylindrical shaft grinder. When he gets closer to the end, he'll make much more frequent measurements, and we'll make sure that this thing lands on the exact specifications. Again, tolerance is 3/10,000ths of an inch, right? That's 4 decimal places. Rhodesy will nail it. Again, he'll leave 1/10 possibly for a hand polish, and then once he gets this thing dialed in, we'll move it over to the shaft straightener and the balancers. We'll follow this thing through the process. Step 2, turbine wheel. So we did the grinding undersize. We've done the polish jobs. The material that needs to come off of the shaft has been removed. The next step is the straightener. These things turn pretty rapidly. Even this old pig, you might be talking 20 or 30,000 RPMs. Straight shaft is a critical recipe component for a long-living turbo. Balance is critical, and shaft straightness is critical. This old dog looks kind of crude, but this is an extremely precise hydraulic press. You can see there are 3 different dial indicators chucked up on the shaft. We're going to rotate the shaft in these fixtures, read the indicators. Again, we're down in tenths, so 4 decimal places. We're reading the straightness or the run out on the shaft. I have no doubt that if I were to attempt this, I would immediately destroy this component. Again, this is unobtainium. Makes me a little bit nervous to watch these guys straighten this shaft, but they're going to do it. All right, it's chucked up. We're going to watch an expert spin the shaft, read the gauges, mark the highs, mark the lows. You'll see him slide the turbine wheel back and forth. Down here's the business end, so you'll get to see him give her some beans, and we'll straighten this thing back out. Once we get it straight, we'll take her down to balancing. We'll step back again and watch the experts perform their craft. Tail fired up. He's giving her a spin job. Again, marking highs. So he's made his reading. Dial in how much pressure he wants to give her. Give her the beans. This is touch and feel and experience. So we put a little pressure on her. Slide her down to the next high. There you go. And then we'll spin it, check it again to see where we're at, and then we'll likely chase our tails a little bit. We'll just keep going after the highs, right? Knock down the highs, read it again. Looks kind of crude, but shaft straightness is mission critical. We'll get out of his hair, not apply any pressure, let him finish getting this thing straightened up, and then we'll take you over to the balancer. We'll bring you along. Step 3 in turbine wheel reclamation, also using a machine that I know nothing about. This is a Heinz balancing machine. It also is from an era before, but this dude is also extremely precise. Doesn't look like much, but it is. More so than shaft straightness, balancing is a critical component for a quality repair, and this is where it happens. This is the balancing machine. We've got a turbine wheel chucked up in it right here. We also balance compressor wheels, or we'll also balance them as an assembled unit. Compressor wheel on the shaft, potentially the thrust components chucked up in it as well. For sake of video, we're going to show you the turbine wheel, all right? Again, this thing's one of those magic boxes. I don't fully understand how it works. I know that you use some of these dials over here to tell the machine the characteristics of the turbine wheel, diameters and lengths and weights and things of that nature are dialed in on left and right plane. We've got a book here from before I was born for this wheel that tells us what some of these readings should be. The wheel is chucked up on these rollers, and it's a little bit floppy in there, okay? What this thing does is it detects the high spot. So when we get out of the way and shut our mouths and watch a professional do this, he's going to take some of this schmoo and he's going to stick it on the wheel. That's going to dictate where the high spot is. He's going to hit the contact button and run this thing up, and he's going to dial it in so the strobe light indicates the high spot or the heavy spot that we have influenced with the tacky weight, okay? Then we're going to pull the tacky weight off, and we're going to run it again, and that's going to reveal the true heavy spot. Once we learn where the true heavy spot is, where the imbalance is coming from, we're going to take the wheel out of the fixture. We're literally going to walk it over to a grinder, and we're going to remove material from either the left or right plane, depending on the readings, and either a little bit or a lot, and even a lot isn't much in this context. We're going to knock some weight off of it with a grinder. Once we do that, we're going to bring it back over. We're going to chuck it up again. We're going to run it again, and we're going to find the next heaviest spot, and we're going to be able to tell on this gauge how heavy that is. There's a specification for imbalance, and we're going to get beneath it. That's the goal. Get the imbalance out of the wheel so that when this thing goes back together, she hums along beautifully. So again, we're going to get out of the way. We're going to watch an expert do the balancing. On with the sticky weight. He's going to run her up. He's going to dial in the speed. The speed is what determines when the strobe lands on the sticky weight. So he's trying to get the sticky weight at 12 o'clock. It's kind of like an ignition timing light. From the backside, you can see that he's got her dialed in at 12 o'clock. That's step one, kind of a calibration for this machine. Get the light landing on the heavy spot. Now, pull the weight off. You want to make absolutely sure that you get all of the sticky off of the wheel, because if you leave some introduced weight on the turbine wheel, it'll throw your reading off. Weight has been removed. He's going to run it up again, and he's going to turn the strobe on. He's reading the gauge to see how much imbalance he has. and he's looking at the back of the wheel, and you can see some of the prior balancing marks. So that's how he knows where to go and remove some materials. He's going to walk it around. He's going to mark it. That's where it's heavy. Run it again and verify that his mark is at 12 o'clock. It dances around a little bit, so you kind of have to take an average, but he's got it nailed. It is on 12 o'clock. I don't know if that's picking it up, but you can see his mark right there in the 12 o'clock, halfway up the back of the wheel. And he's also checking the left and right plane. Both sides of the head of the turbine wheel are being measured here. That's the first step. Now we know where the heavy spot is. We'll move it over to the grinder. Look at the grinder that we use for removing material from these components. Well, this is not the one to be using to sharpen your drill bits or grind off your weld splatter, right? This thing's got a little bit specialized wheel. This is only for shaft and component balancing. We're going to take a little bit of material off of this one and we'll run it again. That's it. That's all it takes. So you saw it. Pulled some material off on the grinder. Put a little schmoo on the bearings there. Got her wound up to speed. And now he's got the balancer engaged and he's reading out on that dial how much imbalance is there. He cut it down to a fourth of what the imbalance was before, and he is in specification by twice as much as it should be. So turbine wheel balanced. This thing is ready to go. We'll clean it up and do just a final inspection, but this component is ready to be handed back to the build-up rooms. We're back in the machine shop for the bearing housing work. This is a Milltronics ML22 flatbed CNC lathe. This is where we do a lot of bearing housing and end housing work. We've already got this bearing housing chucked up in the spindle. That's Matt's bearing housing. That's the one that was worse for wear. This is the bearing housing out of Plan B. So Gary's already got it chucked up and dialed in true. We're going to use a boring bar with a carbide insert specifically for cast iron. Again, we spoke of this step at the counter, right? This one's not exactly traditional design. Usually we would just come through with a hone, smoke her out square, and we'd be good to go. This one's got this step that we discussed, either machining out and putting a snap ring groove, or what we're going to do, boring bar, we're going to walk up to that step and we're going to skin the idea of this bearing housing. He's got her touched off and dialed in, and he's operating in conversational mode. No program from the development office. He's doing this one right on the keypad. We're going to get out of the way. We're going to watch this thing get cut back to factory spec. All right, so here he is chucking up the bearing housing in the lathe. Once he likes the way he's got a hold of it, he's going to start taking some readings, making sure we've got it dialed in. Got a test indicator on a mag base. You'll see him check it in the X and Y directions here. So rolling it around, watching the highs and lows on the indicator. Give her the attitude adjuster. Knock it around, spin it again, look for the highs and lows. Shooting for 0. Looks good in that direction. Going to torque her down in there. Flip the indicator around and read it in the other direction. 3-jaw chuck, but it's adjustable. So kind of like you've seen A-bomb doing the 4-jaw thing. This is an adjustable 3-jaw. So just roll it around. Check the highs and lows, knock down the highs, loosen the lows. Make an adjustment, roll it around, check the indicator. Nailed it. Now he's got the bearing housing chucked up, zeroed out, and he knows where it is. Now the next step is we have to tell the lathe where the bearing housing resides in relationship to the tooling. Zero it out, if you will, hone it in, however you want to say it, but we got to tell the lathe where the part is. So he's already taken a measurement. He knows the distance from the outer face down to the step. So really he's just looking to tell it the diameter of the bore and the location of the outer face. Looks like he's running a reference tool. He probably knows the diameter of that little widget, and he's going to put it in between the tool and the part and then compensate for that on the dial pad here. So he just dialed in 1/4 inch. So he is in programming mode now. He knows the dimension of the current bore. He's told the machine where the bore is located. He's told the machine what the bore measures, and he's told the machine how much he wants to take out. I don't know if the camera's picking it up, but you can hear it just faintly cutting. So we're taking about 5 thousandths a pass here. And again, because of that step, we're not going to get the opportunity to run a hone. So we're hoping that the surface finish with the boring bar is acceptable. If not, we might reach in there with a piece of emery or a piece of Scotch-Brite, maybe give her a polish job on the lathe. And if that doesn't cut it, then we're going to have to smoke that step out of there and take it to the hone. Take a look at her, the snap ball gauge, so he's going to take a measurement. Tolerance on this dimension is 1/2 thousandths, so 5/10 thousandths of an inch is target. Snap ball gauge in a micrometer. Now we've taken a measurement after the first cut. He's back on the conversational mode. He's going to update the location of the bore and the diameter of the bore. And when we come in for the final pass, there's no guesswork left, right? We now have a true cut with this bearing housing fixtured in this machine with that tool located where it is. So now that we've updated that information, we're going to come back in for the final cut. And somewhere around 5 thousandths, taking it easy on the feed rate. Again, we're taking 5 thousandths across what is probably a 1/2 inch journal. So this is not, hogging a bunch of material. This is pretty precise. And again, we've got a tolerance of 1/2 thou, which is pretty generous for us, right? That should not be an issue to hit. So. All of that setup, all of that blabbering for that right there, right? That's going to be what saves this turbo. So he's got that journal dialed in just to make sure we've nailed it. Once we get it off the machine, once we've ensured that he's good to go here, before he takes it out of the chuck and moves anything, he's going to want to make sure he nailed his dimension. Over to the micrometer, all clear, journal bearing salvage. So you just skinned that journal out. He's looked at it, surface finish is fantastic, dimension is spot on. The real test, this is the 10 thousandths oversized journal bearing. We've been talking about this throughout the entire process. The clearance or the tolerance between the OD of the journal bearing and the ID of the bearing housing is about 2.5 thousandths. He's measured the bore. It's spot on for a 10 over bearing. And we're going to do the layman's test, right? Is this going to fit in the hole? And is it going to slop around? Here we go. The bore is right here. Slides in perfect. Nailed it. So that was side number one. Now we've got to take it out of the machine. We've got to change the jaws. We've got a totally different fixturing on this side. We'll flip it over, dial it in again, and we're going to come in from this side or the other side, skin that journal bearing out, repeat the process. Critical component of this operation is we don't only have to make sure that we're centered on the bearing housing, but we've got to keep the journals in line with each other. We can't have them stepping apart or tilting away from each other, right? They have to be parallel and directly in line with one another. We're going to get out of the way. Gary's going to flip this thing over, skin the other journal out, and then the world will be saved. Gary's got the bearing housing spun around. Looks like he's got the indicator dialed in on it. Again, that side of the bearing housing had a good known register. It was original factory fixturing and machine areas. He's chucked up on that. He's dialed in on the back. I would guess at some point he'll come around and reach in and touch the journal that he's already machined to ensure that we've landed correctly. If the journal on the backside that he's indicating with was machined in the same operation as the face that he's indicating, and if the journal that he's going to machine on the outside was referenced from it, then we know we're going to land back straight and we're going to land parallel and on the same planes. It's mission critical that those line up. Same thing on this side. He's got the part chucked in the machine tool. He's got it indicated running dead center on the bore, and then he's got to come over with the tool, and he's got to tell the machine where the part is in relation to the tool. Again, we're doing this through conversational programming right here on the keypad of the machine, and he's coming in, going to touch off. He's also got to tell it where that step is. We can't blow through that step. That's what holds the journal bearing on the inside of the bearing housing. He's using the hand pad there, and he's just coming in and skinning a flat surface. So he's got to get a flat surface while it's in the machine so that he can tell the machine tool where the bore is and what size it is. And he's got a depth mic here. Reach in and touch that step so he can tell the machine where that step is. He knows some dimensions. He knows where this component is located. He's telling the machine where these things are, right? Again, we can't smoke that step. Just like the other side, this is first cut. So he's got it dialed in. Once he gets the first 5,000ths out, he'll come in, take a measurement. At that point, we know the gospel. We know the dimension. The machine tool knows exactly where the part is. Turbine housing side of Matt's bearing housing. This journal was the worst condition, and we've cut 5,000ths, which is generally enough to clean up a normal failure. Still got grooving in the journal, so it's cleaned up enough where we can get a good measurement, enter those particulars into the programming. The machine can tell from there exactly how much more to cut off to get us to land within specification. The practice cut, the cut to tell the machine tool where the part is, was right on out of the gate. Because we were piloted off of a known good surface and in line with the other bore we've already cut, it would stand to reason that that cut would have gone well. Final pass. Theoretically, there you have it. Looks like it cleaned up, so we're going to take a look at the finish, make a final measurement, make sure we nailed it, and this thing is almost ready to go back into service. Right on the money, says the man. Fantastic. We brought you through the process of saving the turbine wheel. That's good to go. We ground it 10,000ths undersize. We brought you along for the process of repairing the bearing housing. And again, we took the ID of the bearing housing 10,000ths oversized. So just like you've seen on crankshaft journals, same thing, right? Machine this undersized, machine that oversized, and then we've got a custom bearing to make up the difference. The clearances have been restored to factory specification. The components have been inspected, and we are confident that they're good for another cycle of life. Turbine housing, not super proud of what we've got going on here, but there's nothing we can do. This is real world situation. This turbine housing cannot be sourced. If it could, I assure you, we would get a new one, but there are no used ones out there to be had, and that's not even considering the condition, right? We didn't say we want a good used one. We just said any used ones. None. There's none. This is it. We brought you through some of the process here. I think there was about 12 holes. The hardware was busted off. Set them up in the old Bridgeport, knock them down, drill them out, Heli-Coil, and repairs. In the big picture, in the grand scheme, the hard part is done. We're going to take these components back up to the build-up room, and we're going to spread them out on the table. We're going to ensure that they are spotless and clean, Appearance is good. Final inspection. We're going to get some components. We've got journal bearings here. We've got some more parts up there. And we're going to slap this dude back together, and we're going to send it back to Matt. We're back up in the assembly area. Couple of updates that we didn't bring you through in the machine shop. The bearing housing out of the Plan B turbo was scrap. Says right on there, no good. We had this chucked up and we had too much run out in this flange in that direction. It would not pass inspection. No good on that one. The outlet flange, we showed this earlier. It was cracked here. No good. Drew it up. We had the neighbors next door run this out on the water jet. We've got a new flange. I don't know why they've only got 2 holes in this flange. There's 4 holes in the turbine housing. I would have put 4 holes in it, but we don't know if the application has some type of interference. If needed, Matt can pop those out easy enough. The turbine housing, we did one more operation here where this flange mates up. So this dude goes there. That's where your exhaust system connects. On the turbine housing out of Plan B, we faced this area, so we've got a good sealing surface. And then we came in on the backside where it bolts to the manifold and did some cleanup work there. This is the turbine housing out of Matt's turbo, also no good. So we'll move it down to the junk pile. This is all scrap iron. Everything else on the table is ready to rock. We're going to get back out of the way and we're going to watch an expert slap this thing back together.
Let's build a turbo. Here's the vane like. It goes in. It gets these lovely wedge bolts. Alright, so those are well in place. We replaced the gasket for the little shim that's on the outside.
So those wedge bolts capture the nozzle ring, and the nozzle ring in this configuration is interchangeable and is what dictates what we call the AR of the turbine housing or the flow characteristics. You can swap that out to kind of change the performance. It is the original variable geometry, even though it cannot be varied.
Correct. Alright. Alright. At this point I'm going to install our shims. The original shim, if you remember when it came out in the video, they were all rusted and corroded. We have these made for us. These are kind of hard to come by. I can go ahead and...
This is also the material that we machined off of the face of the bearing housing where it was not true. This is what we have to use to make that back up. So
correct. And then this is a heat shield. I'm going to go ahead and install this piece here, and I can set that piece aside. Next is getting the bearings all installed into the bearing housing. Here's where he was just talking about where we machined the face off. This bearing housing compared to the old one, when tested, although looked worse, it actually functioned much better. So that's why it was retooled to be reused. Just giving my surfaces a wipe down. We coat stuff in a coating oil so that way they don't instantly rust. We had to cut the bearing housing out tin, and we had to also grind the shaft of the turbine wheel down tin. So my bearings, we call them tin. And that's to make up the material that was removed in and out. I give them a good coat of oil, and that just slides right on in there. Next piece is it's a very small thrust bearing. And it goes, it's pinned. It pretty much only goes in one way. If we were to put it the other way, it would not be aligned correctly. Then we have what I call a flinger. It's also sometimes called a slinger. It cleaned up pretty well. And then we have a new piston ring. So I'm going to put the piston ring in its groove. We replaced the original seal plate. It had damage here where the original slinger had pushed up into it. So that just kind of snaps up in there. Feels good. Alright, I'm going to put a little bit of oil on the top of my thrust bearing. And then there is an oil hole. This is where your oil comes in. That hole aligns with the hole on the seal plate. fill out the oil to get there.
If you don't align that, she will not last very long.
The turbo will burn up,
Self-destruct.
very quickly, within moments.
These are the components that were the root cause failure of this thing, right? So we discussed oil contamination before.
Yes.
And these are the components that took the brunt of it.
I got some better shims that go here. It's just held down by these 6 bolts. I like to hand tighten most of my stuff down, so that way, what I don't want to do is just tighten one side. It could then kind of make the seal plate cock, and even though everything will tighten down, it's not sealed flat and true. And then later in the stack, it could just cause issues. So just trying to get it right here pays off in the end.
The proverbial star pattern, just like you mount your wheel back on your car, right? You don't zip one down and then
Yes, correct.
torque it all the way, right?
That is
Get
correct.
them all snug and then come back.
Yep.
So I walk them in.
Yeah, I do that pattern a couple times to make sure they get a little snug as we go. I'm just going to torque them to it's about 120. It's good. That's good and tight. Then these were installed with these. I call them bendy tabs. And then I'm bending this tab back up. This helps these bolts not to back out of themselves.
Technical term, bendy tab.
Technical term, bendy tab. I think so. The correct term is lock washer, but I mean,
I'm with
fun.
you.
It's fun. Bendy tab. I think everybody understands that a little better, maybe. I see a lot more of these type of tabs, usually on the turbine housing, and it's just the vibration of the turbo.
Usually external to the turbo. But you could see if those bolts come out inside the turbo, you're going to have a bad day.
That is also very true. Alright, so those are all been bent up. We're going to flip it over. What I call the top bearing, it's the turbine side bearing. It's the hot end. Same with the last. I'm going to coat it with oil. Just kind of slip it in there. This side gets a retaining ring. The other side did not need a retaining ring. When the way it was stacked up, that thrust bearing, when it's pinned down, kind of hold that retaining or that journal bearing in place. On this side, it does not have anything to stop that. So if we just put the wheel in there, that journal bearing would lift up. And
so the inner edge of the bearing is retained by that step that we've discussed. When we were talking about machining the bearing housing, it had that step, which is a little bit unique to this style. Usually there's a snap ring on the inboard side and a snap ring on the outboard side.
Yes,
but the inboard retaining feature is machined into the bore of the bearing housing.
That feels pretty good.
Bearings are captured. Journal bearings are captured.
Correct. Next is our diffuser plate. It's a unique vane system setup, I guess, on this as well. You don't normally see helping airflow on both sides. It's usually just on the turbine side.
That feature is long since obsolete, right? That's discontinued. It's no longer something you see in a modern turbo.
Yeah, I have nothing on a modern. Even the newer VGTA turbos and all those, it's all in the turbine housing. It's not over on the cool side. So as we tore it down, we did mark the housings. What I am actually doing, I've realigned it. And yes, because there's 4 bolts here, if I change it, it will change how our oil inlet and our discharge align to the outer ring bolts, which then can change the orientation when it's placed into the compressor housing. We're going to give it back to Matt, so he doesn't have to do any extra hard work.
Right. Yeah. So it's important that you pay attention to the correlation between these components, because if you do not, Matt goes to bolt this on the engine. The oil drain is pointing up, not at the lines, or the compressor discharge is not pointing towards the intake piping, right? So way back when we first started this project, they took a chisel and they whacked some lines into all these different components so that when this day came, we knew how to put them back together.
Yes, and that's something we do when anybody sends their turbo in for us to look at. That's usually step number one, is please mark the housings. That way, later down the road, if it is repairable, we can do that. The customer won't have to do any more extra work.
There is an orientation specification outline in the manuals on this, but oftentimes the expectation is that the orientation is changed on engine or on job site, so we always mark the way that they were when they came in. It is common practice in the turbo replacement world to have to reclock one of these housings or two of these housings, right? We get the phone call every week, hey, you sent me the wrong turbo.
Sure.
And no, we didn't. That's the way it's supposed to go out. And when you hang the turbo, the expectation is that you do the housing adjustments. So
yes,
we try and nail them when we know, but oftentimes we don't know what they're going to go on.
I do these bolts and any bolt that takes a back plate similar how I did the seal plate. I take them down just where they're kind of snug, and then I do another crisscross or star pattern determining our bolts. Same reason. We don't want it to be slanted anyway. We don't want to just bolt all to one side. It all can just, in the end, cause issues, and it could just be right here just because you try to go a little too quick.
Kind of like building a house. Start square, end square, right?
That's
if you lay the foundation and she's callywhonked, when you get to the finish line, you're going to have to take it back apart. So.
I took these to 150. Pretty good. All right. Almost have a cartridge built up.
So cartridge is what we call the bearing housing and the wheels in an assembled state. Some folks call it a CHRA, center housing rotating assembly, or a cartridge, and it's a common service process, right? So the end housings are just boat anchors, and if your turbo fails in the field, you can slap a new cartridge in your existing end housing. So
right. So this is called a diaphragm. It's similar to a heat shield. It sits here. I just have those there to help align, and then this particular one kind of gets a just large nut spun down on it. Most heat shields, well, most turbos don't, and newer stuff don't take a lot of diaphragms, and so most heat shields just kind of sit there. They might have a retaining ring on top, but not many like this. What I'm checking here is I want to know that this large bolt is equal or flush to this surface, so I'm going to tap it a little tighter. It feels pretty good. There is a very small shim that's part of it, and it kind of gets lifted up into this place here.
Technical term, bendy tab.
Bendy tab, except it's more like a bendy shim, I guess.
Bendy shim.
Bendy shim. And its purpose is just like the bendy shims, the bendy tabs. It helps that if the vehicle is gyrating it enough on application, it won't work itself backwards.
Yep, locking mechanism,
yeah.
Right? Retaining feature.
So here we have our turbine wheel. Newer turbine wheels actually take a piston ring. This style, these old turbos don't actually have a piston ring here. So all I'm going to do is lube our shaft up, and then I'm going to go get our compressor wheel.
Well, this kind of goes to show that back in the day they didn't even have a seal on them. So we've talked many times about, hey, my turbo's leaking oil, I think the seals are bad.
Right.
And it's highly debated topic, but the seals are not really what keeps the oil inside the turbo. It's the differential in pressure, and the piston ring is just kind of a suggestion that it doesn't leak, but
very important piece. It's just called the shim.
The shim.
The shim.
So we talked about this before. This is what dictates the position or the depth of the compressor wheel into the compressor housing.
Yes.
So,
all right, you gotta get the wheel.
All right, so the assembly of this turbocharger calls for a preheat on the compressor wheel, so it's kind of an interference fit, and the compressor wheel is in the oven right now. We've got a guy going after it. We've got the majority of the cartridge assembled and fixtured in the turbine housing holding fixture. Moments from now, a hot compressor wheel is going to come flying in here, and hopefully she slides right down on the shaft.
That's the hope.
Got some movement on the other side of the bench, and there comes compressor wheel. So,
Ooh,
bingo, bango.
Bingo. Lovely.
Yep. Slid right on.
Slid right on. Okay, I'm also going to be putting Loctite, and there's also a washer, another important piece. These are just little washers. They help keep everything locked in place.
Don't want this thing to come tumbling out of the fixture. As you're well aware by this point, this is unobtainium stuff.
Yeah, so if you would like to hold on to that, I'm going to take it to torque now. So that's a good sign that it spins. That means that so far nothing that we've built up is causing any type of lock.
Now we have a cartridge.
Now we have a cartridge. A cartridge is a wheel-to-wheel completely built up. Our next up, if you want to give it a name, it's the Supercore.
Again, he's looking for the orientation marks because this thing needs to go in a particular position.
Correct. And I would like to show the marks if I can. So here was the marks that we believe our teardown guy did. I believe it was Val who tore that down.
Yep.
And so these marked up. When I tear down a turbo for R&R, I mark it to our oil inlet, which I've written here because I want to be 100% sure on this. Put some bolts in, and it's just like seal plate and the diffuser plate. I'm going to get them hand tight, make sure everything lines up well.
They did not scrimp on the bolts in this connection. There's, I don't know, 16 of them there?
Okay, let's see here. There were
12
studs that had to be replaced, plus 12 bolts on the outer ring. None of them were good out of a teardown. We do try to replace all bolts. It's good practice.
Yep.
I want fresh
hardware.
Yeah. Okay, so those have been tightened, torqued down. At this stage, I like to give it a spin. I don't feel any binds or anything at this point. I am going to install a drain plug. I just like to do that now. And then we have our turbine housing. Core into the turbine housing to turbo. So here we go.
She's getting some heft now. You can see he's also paying attention to the orientation again. Yep.
And I'm going to check my orientation. I did make notes. Oh, good. Okay. I'm also giving it a spin to make sure that while it's in here, that we put enough shims. The T line, T14 and the T30s are what I know. If you were to get to here and our wheel is hitting, take it back out, gotta add another shim. Put it back in, we would tighten it, and we would repeat this process.
Also, those two mating surfaces that he just joined together have been machined on, right?
Yes.
Even if originally it called for 30 thousandths, when we fixed that bearing housing, we skinned 60 off the face, and I think they went in and touched the mating surface on the turbine housings. He made a educated guess when he went together, when he started the inspection and reassembly process and the measurements, and then predetermined what that number of shims would be. Would you end up with three?
I ended up
two
with
fatties and a skinny in there?
Correct.
Yep.
I believe when the book talks about it, the fatter ones are 20 thousandths and the thin ones are tens, but we had created it with 30 thousandths. And then this process is just like everything else. I'm hand tightening bolts, then I will go back around and make sure everything's seated correctly. also bendy tabs.
Bendy tabs. Can't get enough of them. So if you have the turbine wheel too far away from the turbine housing, you'll lose some of the ability for the exhaust gas to drive the turbine wheel.
Yes.
On the other end of the spectrum, if you don't have enough clearance, then the turbine wheel can come out and contact the turbine housing. It's important, right? You don't want either of those situations. So you can see some of those studs reaching up and impeding the oil inlet and outlet. The final step of this, or one of the final steps, once he gets this thing tightened up, be to come back and lop off the top of those studs.
Yes.
But before we go to lopping, we want to make sure that this thing builds out correct. So
Yeah, you don't want to do all that now, then find out later. Wait a minute.
you also want to make sure that you have those oil connections plugged before you go to grinding and shooting sparks into this thing, right?
Yes.
Contamination is why it showed up. We don't want to contaminate it before it even leaves the place. So.
Correct. Yes. As seen, I had plastic trays to keep my parts in. I try to keep anything that could become a contaminant to stay away. And that's from my bearings, my thrust bearings, any of the internal parts.
Yep. Yeah, a little bit more cleaner operation here in the build-up area than it was. Yeah. You guys saw the dungeon out there in the teardown.
Oh yeah.
You don't want to be assembling turbos out there. It's full of contaminants. And
yeah, I walk out there and I'm instantly dirty somehow.
Yep.
All right, so I tightened every other one. Now I'm just going to go in reverse order and do the exact same thing. I'm checking my wheel as I do this because now that we're tightening it, we are bringing it down onto some shims. We just want to make sure that we still have clearance.
And that's an important thing, because if it's making contact and he doesn't know it and he's winching it in with the bolts,
yes,
it's going to damage the turbine wheel.
Yeah,
so
we definitely don't want to do that.
You can see him as he goes. Every so often he'll reach in there and give it a spin, just make sure it's still free.
And that also helps me, like if I know that if I tighten, say this one here, and it locks, then there's possibly an issue.
It could be cocked.
Yes.
Yep.
So
yeah, this model, this era, this technology, these are a little bit cantankerous builders sometimes, right? The newer stuff, when the components are more fresh and the machine surfaces are still pristine, right? Those dudes slap right back together.
Oh yeah, these can be. This wasn't too bad, but we did do a lot of work to it.
Yeah.
Not that we don't do a lot of work to the other ones, but they can still be kind of a drag.
So this is why he was so cautious when he first started going together, that he had things square and true, because he doesn't want to take it apart again if he doesn't have to.
No.
So he knows he's had to take them apart before. Pay attention out of the gate. Start off square, end up square. So
yeah. They don't get any lighter as you go.
No.
It just gets heavier. At this point, I still got to spin. Got my oil in over here. I'm going to rotate it. Well, when it's on the vehicle, it would be spun a little bit more for the foot. I'm just getting a feel for it. It feels very nice. I'm going to put a little oil in the oil intake, but not much.
What do you got in the container?
So I like to use Lucas oil. It's good for your engine, but also it has just the right amount of tack that when building some stuff, it can help just
Heavyweight.
Yeah.
Heavyweight and sticky. Stays where you put it.
Right. And that's
Prelude's important as well, guys. And some of these turbos, even from manufacturers today, come from the factory dry. And if you don't get oil to them real quick and fire up the engine, it'll destroy the turbo. So we always throw some in it while we're assembling it.
Yes.
We are advocates of pre-lubing it on the engine before you fire it up.
Yes. Hopefully when Matt gets his back, he pulls the cap out, he puts some oil in it, and he just works in it as well. I could fill this all the way up, but it's got to go all the way back to him, and we don't want it to ooze out.
It'll leak out before it gets there. Again, this thing doesn't have the pressures that are keeping the oil in it at this point on the bench. And by nature, I know we discussed it a little bit earlier in the video, but by nature, this thing is going to leak a little bit until it soots up and until he works the machines. So we've discussed it with Matt, right? You need to change your oil, and you need to put this thing on and kind of go to work fairly quick. Get some heat in it and get some drive pressure behind it.
Yeah. So I put bendy tabs. It also has lock washers, so I'm just going to see if I can bend our tips up just a little bit. And then there's a few other things that we'll do, and this will be good. Like as I said, We'll cut the tips of our studs off because it does feel great, and I think we're good here.
One of the last pieces of the puzzle is to dress her out. One of the few remaining supporting suppliers out there is, in fact, Caterpillar themselves. They don't have a whole lot left for this pig. They do have the installation components.
Nice.
I will tell you that this box of seemingly simple components, 3 gaskets, and 6 O-rings probably costs about as much as your average turbocharger today.
Wow.
Brace yourself if you're going to go there, but these are unique to this turbo. This turbo is 60 years old. Caterpillar does still support these components. They are proud of them. We'll pop these on. We'll ship out with the turbo the oil inlet, oil drain, and foot gasket. We'll throw the O-rings on the compressor cover, and we'll move this thing on to the next step. So the master is done. The last step of the process is to identify this component. Down the road, we want to know, we want traceability as to how we fixed it, who fixed it, what components went into it. This is all documented in our business system, and the next step is to identify this component. We're going to go over to the laser. We're going to engrave a data plate that identifies part number and serial number, which again would lead us down the path of how we arrived at this component when we serviced it. So we'll do that. We'll tag this thing, and we'll take you back up to the parts counter, and we'll get this thing out the door. Long process, right? But we've reached the end. At Area Diesel Service, one of the many cultures is do the best you can, right? And that's what we've done. You guys watched it. We don't have to go back over it yet again. We've got an amazing crew back there. You guys saw the process. Given the circumstances, given the component availability, this is the absolute best job that we can do at Area Diesel Service, and I'm proud of it. These guys nailed this thing. This is kind of undoable work. These guys whipped this thing back into fantastic shape. That's where we're at. I'm proud of the crew. Give them a thumbs up. Give them a like. This thing turned out fantastic. $1 million question. Summarize, what did it take? We had 11 different people touch this thing throughout the process. Those 11 people account for 227 years of experience. It's one of the values of Area Diesel. We've seen this stuff before. About a 20-year average level of experience for the people that contributed to this repair. You saw many pieces of equipment. We didn't show everything, but lots of expensive stuff required to perform this repair. You saw the Milltronics, flatbed CNC lathe, laser engravers, the things you don't even think about, right? Forklifts, bake ovens, Bridgeport, shaft grinder, shaft straightener, balancer. Roughly speaking, we tried to think about the equipment that we used. Well north of $500,000 of equipment were utilized in the repair of this turbo. A little bit of overhead to kind of give this thing some scale. To summarize the expense, the question that everyone is wanting to know, what did it cost? And we've got a list. We had $215 in some custom shims. $625 was the teardown, disassembly, cleanup, preliminary inspection, $625. The Plan B core, $500. There was a bag of gaskets from Caterpillar. That was $175. We had to make a discharge flange. That was another $100. Kits, bearings, internal components, $260. The thrust plate that was smoked out of Matt's turbo, $185. Hardware and Heli-Coils, $40. The trip through the machine shop, big line item here, $1,600 to perform all of the machine work and repair on the subcomponents. And then we had another hour of labor to put the thing back together. Grand total, $3,825 to fix this 60-year-old turbo for what is likely about a $3,825 bulldozer. That's why you don't see too many of these at Area Diesel anymore, but occasionally they still roll in. We'll drop you a link to our merch store if you want to check out some Area Diesel swag. Again, if you see opportunities for us to collaborate with other YouTube creators, tag us in a comment, take a screenshot, shoot it over to parts@areadiesel.com. We'll send you out some of that sweet Area Diesel merch, no charge. If you do need any of our services and you mention to us that you learned of us through this collaborative content with fellow YouTube creator Diesel Creek, we'll send out your project free of charge on the shipping. And if you need anything, don't hesitate to reach out to us. We pride ourselves on taking good care of folks, providing a high quality customer experience. You can send us an email at parts@areadiesel.com. You can log on to our website at areadieselservice.com, where you'll find a large amount of high quality information. You can chat with us instantly through the button in the bottom right-hand corner of your screen, where you'll have immediate access to a diesel engine expert, or you can call us at 800-637-2658, or you can stop by any of our locations in Iowa, Illinois, or Indiana. And the first person that sends us a fax with their name and address, will send you out a hat, right? 217-854-8972. Shoot us over a fax. We'll send you out a free hat. So that's a wrap. We appreciate you watching. We'll see you next time.